Welcome back. Let's learn about velocity and acceleration using vector functions. Alright, so if you remember way back to early on in Calculus 1, we learned that we could use derivatives of functions to describe instantaneous velocity, as well as speed and acceleration for particles in motion, or anything that has a path of motion that can be modeled by a function. Alright, and so we would call our initial function the position function, and I believe in my Calculus 1 videos, I used a function s of t to represent the position function. But more recently in Calculus 3, we have used s of t to represent the arc length function. So to avoid any potential confusion there, I have written the position function as just f of t. But if you take the derivative of the position function, f prime of t, that would give you the velocity function v of t that corresponds to that position function. And then if you take the derivative again, so f double prime of t, or v prime of t, that will give you the acceleration function a of t, which describes the acceleration for the particle in motion whose position function is f of t and velocity function is v of t. Alright, and then I don't think I really talked about this much in my Calculus 1 videos, but you can also find the speed by taking the absolute value of the velocity function. Alright, so speed is essentially the velocity, but we don't care about the sign of that measurement. We just want the absolute value of the velocity. Alright, and it is important to notice here that unlike with our vector functions, which we are going to get to in just a moment, that this t in these functions is not a parameter, it's just the independent variable for these functions. Okay, so you could really think of it as f of x, v of x, and a of x, but we just use t because time is usually our independent variable when talking about particles in motion. Okay, but everything here that we just went over should be a review. This is nothing new, but what we can do is extend this idea to particles in motion whose paths are modeled by curves represented by parametric equations, and therefore vector functions. Alright, in Calculus 1, the curve had to be defined by a function, but now in Calculus 3, we can work with any curve in 2 dimensions or 3 dimensions by using parametric equations and vector functions. And so instead of a position function, we will have a position vector, the vector function r of t that we have been working with for all of our curves in 3D space. And of course, you could use it for 2D curves as well, but our focus in Calculus 3 is mainly 3-dimensional curves. But regardless, r of t is our position vector, and just like in Calculus 1, if we take the derivative of that position vector, we will get the velocity. In this case, the velocity vector, not the velocity function, since we are working with a vector function. And so we represent the velocity vector with vector v of t. That will be equal to the derivative of r of t. All right, so r prime of t is equal to the velocity vector v of t. And then once again, just like in Calculus 1, we can take the derivative of the velocity function to get the acceleration function. In Calc 3, we can take the derivative of the velocity vector to get the acceleration vector. We represent the acceleration vector with the vector function a of t, and a of t would be equal to the derivative of the velocity vector, so you'd have v prime of t, and the second derivative of the position vector, so you'd have r double prime of t. Okay, and then for the speed, in Calc 1 we just took the absolute value of the velocity function. We will do something very similar when working with vector functions, but it is a little bit different because remember, these are vectors, and so the position vector, the velocity vector, and the acceleration vector all have both a direction and a magnitude. Okay, they don't just give you a specific value of the position, the velocity, or the acceleration. They also tell you the direction for each of those quantities. All right, so when we're talking about speed, we're just interested in the magnitude of the velocity, not necessarily its direction. We just want to know how fast is a particle moving. Okay, so instead of the absolute value of the velocity function, in this case, we will take the magnitude of the velocity vector to calculate speed. All right, so speed is the magnitude of the velocity vector v of t. And so that's the main idea here. That's really all that's new in this lesson. We're just extending an idea from Calculus 1 into Calculus 3 using vector functions. And of course, while we will primarily work with 3D vector functions, note that everything that we just wrote down here also applies to 2D vector functions that represent plane curves, okay? But now, let's actually take a look at an example of finding the velocity and acceleration vectors as well as the speed for a given position vector. And so here is our example. Just as I said, we want to find the velocity vector, the speed, and acceleration vector of a particle that moves along the curve, specifically the curve represented by this vector function. And then we want to find the velocity at t equals 2, or the velocity at time 2. The speed, that's what the magnitude of the velocity vector represents. We want to know the speed at t equals 2, and then the acceleration at t equals 2. All right, so let's do that here. Our vector function r of t is equal to t cubed I plus t squared j plus t k. All right, so let's start by finding the velocity vector. Remember that the velocity vector is just equal to the derivative of the position vector. So we're going to take the derivative of r prime of t, which is equal to the velocity vector. And so if we do that, using the power rule for derivatives on each of these components, the derivative of t cubed is 3t squared. So we have 3t squared times I, and then plus the derivative of t squared, which is 2t. So we have 2tj, and then the derivative of t is 1, so we just get plus k. All right, so we found the velocity vector. That's one thing that we wanted to find for this example. But we also want to find the speed, so that would be the magnitude of this velocity vector. So let's do that on the side here. The speed would be the magnitude of v of t. And so remember, the magnitude of a vector is equal to the square root of the sum of the components squared. So we're going to square 3t squared, add that to 2t squared, and add that to 1 squared. So we have 3t squared squared plus 2t squared plus 1 squared. All right, and then simplifying, we'll have the square root of 9t to the power 4, because 3 squared is 9, and t squared squared is t to the power 4. And then squaring 2t, we get 4t squared, and then 1 squared is 1. Now, we can't really simplify this any further. I don't believe that this can be factored in any way, but even if you could, it's totally fine to leave it in this form. All right, that would be the speed or the magnitude of the velocity vector. Okay, so that takes care of the speed. We now found that. Let's move on to finding the acceleration vector. So what we want to do is take the derivative of the velocity vector. So really what we're doing here is taking the second derivative of the position vector, which is equal to the first derivative of the velocity vector, and doing that gives us the acceleration vector a of t. Okay, so a of t will be equal to a vector whose components are the derivative of the velocity vector. The derivative of 3t squared is 6t, so we have 6ti, plus the derivative of 2t, which is 2, so we have 2j. And then the derivative of the z component, which is just 1, the derivative of 1 is 0, so we would have 0k, but I'm not going to write that because the component is just 0. All right, so the acceleration vector only has an x and y component, which is totally fine. That can happen. And so we're done. That is the acceleration vector for this given position vector. And so now we have the velocity, the acceleration, and the speed in terms of t, but now let's find the specific values of the velocity, speed, and acceleration for t equals 2. Let's find each of those values yet for this example. Starting with the velocity, v of 2 is equal to this vector, but where you plug 2 in for each of those t's. So we have 3 times 2 squared times I plus 2 times 2 j plus k. The z component doesn't have any t's, so nothing changes there. But then 2 squared is 4, times 3 is 12, and then 2 times 2 is 4. So just rewriting those components right here, we have 12i and then 4j. Okay? That is the velocity vector, specifically at time 2. That was the next thing that we wanted to find. But now, let's find the speed at time equals 2. And you have a couple different options here. You could plug in t equals 2 into this expression that we found earlier, but it might be easier in this case to just take the magnitude of v of 2, or the velocity at time 2, since we have these nice components of 12, 4, and 1, you're going to get the same answer either way, but I think it might be easier to just calculate the magnitude of this vector right here, rather than use this formula. So the magnitude of v of 2 is equal to the square root of 12 squared plus 4 squared plus 1 squared, right? We take the square root of the sum of these components squared. 12 squared is 144, 4 squared is 16, and 1 squared is 1. So this is equal to the square root of 144 plus 16 plus 1. 144 plus 16 is 160, plus 1 is 161. So we get a speed at time 2 of the square root of 161. That doesn't really simplify to anything else. That is in its simplest form. But if you did want to know the approximate value, the square root of 161 is about 12.688. Okay, but that's not really necessary here. That just gives you an idea of the actual value of that magnitude or that speed, but it's totally fine to keep it in the exact form of the square root of 161. All right, and now one more thing we want to find is the acceleration at time 2. So we're going to plug 2 in for each t and the acceleration vector, and there's only one right here. We'll have 6 times 2, which is 12. All right, so the acceleration vector at time 2 is equal to 12I plus 2j. And that's it. We have now found everything we wanted to find for this example. So overall, not too difficult. These are all calculations that we have done before, but just not within the context of the position, velocity, and acceleration vectors, right? We have taken derivatives of vector functions before, as well as evaluating vector functions at specific values and taking the magnitude of vector functions. Those are not new calculations. We're just doing them within a different context. Okay, so that's it for this example, but I do want to look at another example where we do something a little bit different. If you remember, in Calculus 1, we could also do the reverse of this process right here. We could find a position function given an acceleration or velocity function by using integration, right? We could start with the acceleration function and integrate it to get back to the velocity function, and then integrate the velocity function to get back to the position function. But of course, we also had to be given some additional information that we referred to as initial conditions. But assuming that we have that information, we were able to do that. And we could do the same thing here. In fact, this is an application of the integration of vector functions. Remember when we first learned about integrating vector functions that I said we would leave the applications for later? Well, this is one of those times where we see one of the applications of the integration of vector functions. Given an acceleration or velocity vector, as well as some initial conditions, we can find an unknown position vector as well as an unknown velocity vector for a particle in motion using integration. And so that's how I want to end this lesson. Let's take a look at an example of doing that. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful, then I'd like to invite you to join my membership site, JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. So if you are interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. All right, and so here's our example. We want to use the given acceleration vector to find the velocity and position vectors. And our given acceleration vector, a of t, is equal to negative cosine ti minus sine tj. And then we have our initial conditions over here. Specifically at time 0, the velocity is equal to j plus k, and also at time 0, the position is equal to I. All right, and so once again, just like with our previous example, the type of work we're going to do here is nothing new. It's just within a different context. We have already done examples of this exact type of problem in a previous video, specifically when we were learning to integrate vector functions. It's just that now we are referring to the second derivative as the acceleration vector, the first derivative as the velocity vector, and then of course our original vector function is the position vector. Okay, so what we're going to do here is start by integrating the acceleration vector. In order to find the position vector, we first have to know the velocity vector. All right, and we get the velocity vector by integrating the acceleration vector. We're doing the opposite of what we did before. You take the derivative of velocity to get to acceleration, so you integrate acceleration to get back to velocity. All right, so the velocity vector, v of t, is equal to the integral of the acceleration vector, a of t, with respect to t. So you will have a of t dt. All right, so let's set up that integral. We will be integrating this vector function. We have components of negative cosine t I and minus sine t j. All right, and so remember, to integrate a vector function, you just integrate each component individually. So what we'll find here is that the velocity vector is equal to the integral of negative cosine t. Remember that the integral of cosine is sine, so we will have negative sine t times I. And then for the y component, we need to integrate negative sine t, and the integral of negative sine t is positive cosine t. So we get plus cosine t times j. Now, don't forget, when you solve an indefinite integral, you also need to include your constant of integration. In this case, we would have a vector constant of integration, and I'll represent that with plus vector c. All right, this is where our initial conditions come into play. We need to know what this constant vector is equal to, because without knowing that, we can't really integrate the velocity vector to get back to the position vector. So we need to know what that is, and to do it, we will make use of the initial condition for our velocity vector. Specifically, v of 0 is equal to j plus k. So what we can do is plug 0 into what we have so far for the velocity vector, and then we'll set it equal to what it should be equal to and solve for the vector constant. All right, so v of 0 is equal to negative sine of 0 times I plus cosine of 0 times j plus c. Now, sine of 0 is 0, so this term is just gone. That goes to 0. But then cosine of 0 is equal to 1. So we'll just be left with j. All right, so v of 0 is equal to j plus c. And remember, v of 0 should be equal to j plus k. So let's put that over here. Let's set it equal to what we have now. J plus k should be equal to j plus c. And notice that j is on both sides of the equation, so you could subtract j from both sides, and it would be gone, leaving you with just c equals k. All right, so what we find here is that our vector constant of integration for the velocity vector is just equal to k. So we can put that back into our velocity vector here, v of t, and that will look like this. We're just going to have negative sine ti plus cosine tj plus k. All right, that's what we have found for the velocity vector. So we've done half of this problem now. We found the velocity vector given this acceleration vector and our initial condition for the velocity vector. So feel free to box that in. That is our first answer. But we also want to find the position vector. And so we need to do that whole process again, but where we integrate the velocity vector, right? Because you find the velocity vector by taking the derivative of the position vector. And so to do the reverse, you integrate the velocity vector to get the position vector. Okay, so let's do that here. Let's set it up. Our position vector r of t will be equal to the integral of the velocity vector v of t with respect to t. So write down dt. And then the integral will look like this. We're integrating these three components. The velocity vector is negative sine ti plus cosine tj plus k, and we are integrating with respect to t. And so if we integrate each of those components of the velocity vector, here's what we'll get. R of t, the position vector, will be equal to the integral of negative sine t. Remember that that is just equal to cosine. The integral of negative sine is cosine. So we have cosine ti. Then we want to integrate cosine, which will be sine, because the derivative of sine is cosine. So we get plus sine tj, and then we want to integrate k, or really the component of 1, and the integral of 1 is just whatever variable you are integrating with respect to, in this case t, so we get t times k. All right, but then don't forget, once again, your constant of integration plus c. Or really, in this case, it's a vector constant of integration. So we're almost done. We integrated the velocity vector to get our position vector, but we still need to figure out what that plus c would be equal to. All right, so we want to make use of our other initial condition for the position vector, specifically that r of 0 is equal to I. And so let's plug 0 into our position vector, or at least what we have so far for the position vector. We will have r of 0 is equal to cosine of 0 times I plus sine of 0 times j plus 0k plus c. All right, now simplifying, cosine of 0 is 1, so you'll have 1i. Sine of 0 is 0, so that whole component is just 0. And 0 times k is also 0, so that component is 0, leaving you with r of 0 is equal to 1i plus c, right? That's what this simplifies to. I just continued our work up here. This is all we're left with after plugging 0 into our position vector. And so let's set that equal to our initial condition here. We know that r of 0 has to be equal to I, so let's set I equal to what we found. And we have I equals I plus c, and we can subtract I from both sides of the equation, and so that would be gone, leaving you with 0 equals the vector constant of integration, or really it would be the 0 vector, since we're working with vectors here. And so that vector c is just nothing. It's 0. It's the 0 vector, so we can just ignore it. We can remove it from our answer for the position vector. All right, so what we found here is that our position vector r of t is equal to cosine ti plus sine tj plus tk plus nothing. We don't even need that plus c. Now we can't assume that when we integrate, we do have to check it using our initial condition, just like we did a moment ago. All right, but that's it. We have now found both the velocity and position vectors given an acceleration vector and some initial conditions. Specifically, these initial conditions are describing the starting point of your particle in motion, right? We're looking at t equals 0, so really what we have here is the initial position and the initial velocity of our particle in motion. So given the acceleration of the particle and its initial velocity and position, we found the vectors for the velocity and position, which is pretty cool. And so from that, we would be able to figure out the position of the particle at any time t using the position vector. We could just plug in any value of t we'd like to find the specific position, and we could do the same thing for the velocity. We can now find the velocity at any time t that we are interested in. Okay, so this is a real application of taking the derivative and integrating vector functions. Sometimes for an object in motion, all we know about it is its acceleration, as well as its initial position and velocity, and so from that information, we can find ways to represent the velocity and position so that we can figure out what those values would be at any value of t, not just t equals 0, or whatever value of t is used for your initial conditions. All right, but with that, that is it for this lesson. If you want to get some more practice working with position, velocity, and acceleration vectors, feel free to check out the examples video for this topic that I'll have linked here on the screen. If you have any questions, please let me know in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.